All right, these are the section 6.1 notes. You are going to need to have your textbooks open to page 333. You're going to need at least 2 different colored pens. You can use a pen and a pencil, that's fine. And you're going to need a ruler. Also, at the top of the page, I had written down graphing systems of inequalities, and inequalities were from chapter 5. This is actually graphing systems of equations, so you need to scratch that out and change it a little bit. So a system of equations is 2 or more equations put together. So I want you to look in your textbook and go ahead and turn to page 334. The very first example gives the equations y equals negative 2x plus 3 and y equals x minus 5. There's 2 equations there. They're just sitting right next to each other. That's what a system of equations is. So when you have those 2 equations, we know that we can graph them. And so let's say I start graphing them, and here's my first line, and here's my second line, and they cross. This is where we start talking about the kinds of solutions that these systems of equations have. They can have one solution where they cross at exactly one place. They can have infinitely many solutions where we have 2 lines, but they lie right on top of each other, so they're essentially just the same line. That has infinitely many solutions because it touches in all of the places, because remember, these are supposed to be lines that keep going this way and this way, so they go on infinitely, and they have infinitely many solutions. Or we can have 2 lines that look like this, and they're parallel. They have no solution. But let's say that we have one that has exactly one solution. How would we write down what that solution is? We're on a graph, and we have a point. We would write it as an ordered pair. So when we start writing down our solutions, we write them as ordered pairs. We have different words for to describe the different kinds of solutions. The first thing we're going to talk about are independent and dependent, and consistent and inconsistent. So an independent solution is when there's exactly one solution. So if you have equations that graphed and look like this, it's independent. If you have a dependent solution, it has infinitely many. So if you have your 2 lines and they lay exactly on top of one another, you have a dependent solution. And a consistent solution is when it has at least one solution. So if it has exactly one or infinitely many, it is consistent. If it has no solution, it is inconsistent. I have already written these definitions down. I started writing these things down before I pressed record, so I'm going to read them out loud to you, pause the video as necessary to fill in those parts of the notes, and then we'll move on to the next page. So I changed the first one to equations instead of inequalities. And then a system of equations is 2 or more equations. I underlined one solution, infinite number of solutions, and no solution. An independent solution is exactly one solution. You can ignore this part down here, it's crossed off. A dependent solution has infinitely many solutions. Consistent solution is when a system has at least one solution. It has either one or it has infinitely many. And an inconsistent solution is when a system has no solution. If you're having a hard time either reading those on my page or keeping up with me, those definitions can be found on page 333. So pause the video and go ahead and fill those in. Okay, turn to the next page. This is where that table comes in, and we're going to start talking about the different kinds of solutions. It's kind of tricky to learn at first and difficult to keep track of what is what. So we're going to just fill out our table. That'll make things a little bit easier when you're doing your homework. So if it has exactly one solution, it is considered consistent and independent. And its graph would look like this. You'd have one line that goes this way, and another line that goes this way. And where it intersects is its one solution. And we would write that as an ordered pair. The next one is if it has an infinite number of solutions where it's the same line, and I'm going to do this with a green highlighter and a green pen, so I'm going to show that we have 2 lines but that they lay right on top of one another. So if I have a line that goes like this, and the same line that lays right on top of it, this is an infinite number of solutions. It touches everywhere, both to negative infinity and positive infinity. So an infinite number of solutions. And it is considered consistent and dependent. Notice that both of these are considered consistent. The only thing that changes is independent and dependent. And then we start talking about inconsistent or no solution. And that is when you have two lines that never touch. Okay? Okay. All right. This table can also be found on page 333 if you're having a hard time reading it from the video. So the number of solutions, there is also a little cheat sheet. So if I give you two equations and I don't really want you to graph it, but I want you to tell me, is it inconsistent, consistent, all of those things. Here's a little cheat sheet for you. Rewrite them so that they're both in slope-intercept form, which we know is y equals mx plus b, where m is my slope and b is my y-intercept. Okay. Once those are both written in slope-intercept form, you can look at this and say, let's take a look at my m and my b, so my slope and my y-intercept. Do they have different m values? Yes. Then there's only one solution. Do they have the same n value? And if they do, is their b value different? If their b value is different, which means that their intercept is at different places, you're going to have parallel lines because their slope is the same. That means no solution. If they have the same m and the same b, that means that their intercept's at the same spot and they have the same slope. They're rising and running at the same pace and they start at the same place, so they must lie on top of one another. It has an infinite number of solutions. Okay, turn the page. In order to solve by graphing, which you will have to do on your homework, first thing you do, graph both equations. We know how to graph equations, especially if they're in slope-intercept form. Graph the intercept, use your slope to find a second point, and plot or draw the line in. You'll have to do that 2 separate times, and I would strongly suggest using 2 different colors of pen or pencil so that you can see that you get 2 different lines. After you've graphed them, find where they intersect. If they are the same line, it's an infinite number of solutions. If they never touch, it's no solution. If they touch once, you'd find that intersection, and that is the solution of the system. So let's go ahead and do a couple examples. We're going to graph the system of equations. We're going to and then determine if the number of solutions, if it has any, and if it has one, what is it? So let's go ahead and start. Already in slope-intercept form. So I'm going to make the first line orange. And my intercept is at 10. 0, 10. So I'm at the origin, I go up 10. Okay. My slope is -3, which we can rewrite as -3 over 1, which means I fall 3, run 1. Okay. Then use your ruler to go ahead and draw in that line. Okay, and then I'm going to use purple for my next line. And I have y equals, I'm going to put a 1 in front of here. I'm going to have 1x minus 2, which means my intercept is at 0, -2, and my slope is 1, which is the same thing as 1 over 1. So I start with my intercept, down 2, slope is 1, means rise 1, run 1. Go ahead and graph your point, or graph the line. Okay, I can see these are not the same line and they do intersect, so I have exactly one solution. I'm going to point to that one solution. I'm going to use blue to draw in that solution. This is where they intersect. This is the solution. I write it as an ordered pair. So it has one solution at, let's see, 3, 1. That's it. Go ahead and turn to the next page. I have another solution, or another system of equations that they ask for the number of solutions, and then if it has one, name what the solution is. These are not written in slope-intercept form, so we're going to do this example together really quick. We have 2x minus y equals -1. I want to get it in slope-intercept form, which is y equals mx plus b. And I'm going to start by moving the 2x to the right-hand side. I get negative y equals negative 2x minus 1. I'm going to divide each term by negative 1 because I want to make that y positive. Remember, it has to be each term. Y is going to equal 2x plus 1. That one's written, and I'm going to graph it in blue. Okay, let's go ahead and graph that first, and then we'll come put the other one in slope-intercept form. So I have an intercept at 0, 1. So I'm at its origin, go up 1. My slope is 2, which means I rise 2, run 1. Drawing your line. Okay. I'm going to do my other line in pink. And I have 4x minus 2y equals 6. I want to get the y's alone, so I'm going to subtract the 4x. And I have negative 2y equals negative 4x plus 6. I want to get the y alone, so divide each term by negative 2. And I get y equals 2x minus 3. Which means I have an intercept of 0, negative 3, and a slope of 2. So I'm at 0, negative 3, and I have a slope of 2, which means I rise 2, run 1. What do you notice? You should notice that they're parallel, which if we had not graphed these, we would have known because we would have looked at their equations and realized that they had the same m. And from our little cheat sheet, that would have said no solution. So these don't touch. There is no solution. And that is all we have to write. So I want you to go ahead and I want you to do the examples on page 3 and then come back to the video. I'm going to keep going, so you need to pause the video. So I have x minus y equals 2. Not in slope-intercept form, and I want it to be. So that's the first thing I'm going to do. I'm going to subtract the x. I get negative y equals negative x plus 2. Divide each term by negative 1. I get y equals x minus 2. Let's go ahead and graph it. I have an intercept at negative 2, so I'm at 0, negative 2. I have a slope of 1. Rise 1, run 1. Go ahead and draw your line. Okay, let's do the next one, which I'm going to do in green. I have 3y plus 2x equals 9. I'm going to subtract the 2x. I get 3y equals negative 2x plus 9. Divide by 3 on each term. And I get y equals negative 2/3 x plus 3. So my intercept is at 0, 3. My slope is negative 2/3, which means I fall 2, run 3. Go ahead and draw on your line. Okay. Now, fortunately for us on this one, it intercepted at the same, or at one of the points that we used when we were graphing our 2 points. So I have one solution, and it is at 3, 1. Okay. Let's go ahead and do the next example. First one's already written in slope-intercept form, so let's just graph it right away. I have an intercept at 0, negative 3. My slope is negative 2, which means I fall 2, run 1. Go ahead and draw in your line. I'm going to do the next one in blue. This one is not written in slope-intercept form, so I have to do a little algebra first. I have 6x plus 3y equals negative 9. I'm going to move the 6x to the other side. I have 3y equals negative 6x minus 9. Divide each term by 3. And I get y equals 2x minus 3. So I have an intercept at 0, negative 3, and a slope of 2. oh, I'm sorry, this should have been by a positive 3. This makes a negative 2. So I have a slope of negative 2, which means I fall 2, run 1, fall 2, run 1. And when I draw on my line, it's the exact same as the purple line. Okay, lay right over top of one another, which means it has an infinite number of solutions. All right, that's the end of the notes. Be sure to take a look at the homework, and I'll go over some examples tomorrow in class.